Hey there, Maz. Welcome back for day 332 of me doing Daily LeetCode challenge after each 1 year's worth of green contributions here on GitHub. So today is roster June 13th, 2025. Without further ado, let's get straight into it.
Oh, I see.
Okay, here we go. LeetCode medium problem 2616. Minimize the maximum difference of pairs. Ooh, okay. Minimize is an optimization problem, which means we can usually either use DP, greedy, or divide and conquer. But this is a minimize the maximum. So usually when it's a min of max or a max of min problem, it ends up being some binary search of some sort. So it usually ends up being divide and conquer. Okay, you're given a zero indexed integer array nums and an integer p. Find p pairs of indices of nums such that the maximum difference amongst all the pairs is minimized. Find p pairs of indices. P pairs, okay.
Sure.
Also ensure no index
Sure thing.
appears more than once amongst the p pairs. Wait, what? That's it? 43%.
Physical therapy. Oh. Why?
Oh no, it's pairs doesn't mean consecutive elements, right? Yeah, and it just must be done in no event time.
No.
Right? Yeah. Otherwise, you would just put everything into a like a yeah. So, um, right. So min heap is equal to yeah. The difference is the absolute values. Yeah. So there's probably gonna be some greedy aspect of this. Right. You want to essentially. Yeah, you want to take the p smallest differences and return the p. Basically, you want the pth smallest difference. This is like a k smallest problem. But the pairs. So numbers that are close to each other. Oh, yeah, this is just going to be annoying. Right, because it's absolute value. So like a 1 might actually be terrible. You want numbers that are close in value.
Oh my god, I love this.
Right, because if I do
I started using the templates for
absolute
building
value of nums
our
of I
services.
minus nums of j.
Expensive, but correct way to do so. And I'm using this thing called bicep. And this over here. It's just nice. It's just makes you feel better about yourself. No, it's
Heap of
it's just
0.
our file
Is this the
format.
solution to this
So
problem but just too slow
and
kind
it
of a
gets
thing?
transpiled into ARM templates. Think of like
Yeah, so that's accepted.
it's an
And if we
easy,
submit, this will be too slow,
good
right?
looking way of building Terraform files,
Right.
but like looks like code
Oh, wrong answer.
and it has types and whatnot. I
Uh,
no, we you
what?
could, but we have ARM templates, which is like Microsoft way of like their own templating system for
Oh, is this a p
putting up
equals 0?
resources.
Okay. Uh,
Yes.
if p equals 0, this kind of a thing, and now we TLE?
Yeah, it works. I'm so happy.
Wrong answer.
No, no, no. Terraform reinvented itself for like
Why? Can a pair include itself? Is that what's going on? No. interesting.
What's up? Anyways, I'll let you go, homie. Call me when you get over there with
So the maximum difference is minimized. If it's really like a max-min problem or min-max problem, like usually these are solvable with binary search, right? Where is it possible to have p pairs such that the maximum difference you can tolerate is that much? Why the heck does something like this not work? 3 and 3, 2 and 2. Two and two. Oh, you can't reuse indices, can you? Yeah, oh, okay. Also ensure no index appears more than once amongst the p pairs. Can't you just do this greedily? Right, like we might as well sort the numbers. Right, once we do, like we definitely don't want to take the biggest and the smallest, right? We also can't do this in n squared. Right, the problem is that we can skip a bunch of indices that we don't want. I'm trying to think of two things here. Like one is like being greedy. The second is, can I binary search my way through this like a typical min and max problem? If I set like the difference, like, oh, can you reach a minimum maximum difference of 3? Oh, wait, that might actually be it, right? Because then you can just start going through adjacent pairs of elements and be like, what's their difference? Oh, is it less than or equal to 3? Yes. Okay. Yeah, I think, and then it's just every time you look up if it's better than P, right? Yeah. So we don't even need, we just do min diff. Yeah, something like that. And then, the maximum difference. Are all the numbers positive? What we're going to do is we're not going to do this. We're going to do min of nums. Here we're going to do max of nums. Right? Because like the maximum number of nums, you'll have to subtract something, so it'll actually be something smaller. But we can just ignore that and min difference. Yeah. 0, right? 0 is the best we can do. A max nums. Nice min of nums, actually. Right? Probably can do that. We'll say L, R is equal to min diff max diff. While L less than or equal, mid is equal to L plus R over 2. Get number of oh no, but pairs is anything. Can we leverage something in? Yeah. Maybe this is when you do a min heap. Right, you might as well be greedy and get the smallest numbers and see if they can do it, and then like, next two smallest. And if they can't, then just pop the smallest one. Yeah. So here what we'll do is we'll do a quick sort of nums. We'll say for I in range. We'll say L is equal to this one. Here we don't need this. Here we can do something like return L. Now the only moment of truth is like, does the greedy idea work? No. No, we do. Interesting. We'll say I is equal to 0. Now for now, let's do something. Brand is equal to set. If this. indices. Like that. Okay, that's accepted, but now is this greedy idea actually correct is the question. It is, okay. Completion history 332 days, consistency is key. See ya tomorrow. Okay. Damn. Yeah, this is not a solution I would have come up with myself on my own, where this like 9 months ago or whatever. This is purely just a trick that I've learned from doing daily LeetCodes over months and months and months and months and months. And it's nice to just see it pay off like this. Okay. That's cool. That's very cool. Yeah, this is one of those things where it's like easy for me now, would have been impossible 11 months ago. Damn, that's cheeky. That's cute. Nice. Yeah, I can also probably optimize the indices stuff here. Here we'll just do -1. Last name is 0. That should be a little faster. Yeah, I'm not going to optimize too much, and I'm already past the standard deviation, so I like that. Okay, so nevertheless, as always, in all my videos, I do a cookie cap of values supposed to solve the problem. Here we get a beautiful 69% beats, which is absolutely what you love to see. So for this one, this is really just one of those that I was able to solve just because I've done a lot of daily LeetCode challenges and I recognize this pattern immediately. So the pattern was minimize the maximum difference of pairs. So whenever I come across an optimization problem, right, usually minimizing or maximizing something, I know to always use either dynamic programming, greedy, or divide and conquer. However, a specific type of optimization problem is when you have to minimize the max of something or maximize the min of something. And I've had at least about 5-ish problems that are exactly this pattern inside a daily LeetCode challenge. And each of those, at least one way of solving it is by doing binary search, where essentially you want to minimize the maximum, and usually it's doing one where it's doing one of the mins or maxes is easy to do so greedily, but it's hard to do both, right? And especially in linear time. And so the trick with binary search is you say, okay, I'm going to binary search over all the possible answers that could possibly exist. In this case, this problem asks us to minimize the maximum difference of pairs. Basically, it tells us okay, find p pairs of indices and nums such that the maximum difference among the values at those pairs is minimized. So find p pairs of indices, right? P different pairs of I and j, and you cannot reuse an I and j. For each of them, compute nums of I minus nums of j, all absolute valued, and then take the max of all those. That's what you want to minimize. So what you do is essentially it's okay, what is my possible range of values? Well, my best case is that everything turns out to be 0, right? When you absolute value something, it's going to be 0 or more. The minimum, at the end of the day, this is a minimization problem. So the best result we can do is 0, right? You cannot do anything better than 0 because we're taking the max of a bunch of absolute valued items. Now, what's the worst case scenario? Well, the worst case scenario would be the largest possible absolute value thing, which would be when you take the maximum number minus the smallest number, right? And so here you'll notice that I sort the numbers. I was thinking of doing it with a heap, but then I realized, wait, I just need to sort the numbers instead of recreating a heap every single time. So that just made things nice and convenient. At the end of the day, whether I use a heap inside of my body or I use actually, it's better this way, right? Because here I do n log n work, and here I do n log n work instead of doing no work here, and then O of n log n work log n times. So this would have been in log n time, n log squared n, instead of n log squared n. Now it's n log n because I didn't use a heap. So it's actually better that I just sorted at the very beginning. But that's besides the point. The worst case would be I take the biggest number and I subtract from it the smallest number, right? Because they'll give me the largest possible difference out of any number in nums. When I absolute value, it's still going to be positive or 0. So that's the worst case. So those are going to be essentially my range of values that I can binary search on, right? The best possible case is that the answer is 0. The worst possible case is that the maximum minus the smallest number, right? For example, if there's only p is equal to 1 pair, if nums is equal to 1 and 2, and p is equal to 1, like that's the only pair you can do. Oh well, right? So, but this gives me like a theoretical max and a theoretical min. Now I can just binary search over the values, right? I'm going to binary search through these, and I'm going to go through the leftmost valid solution, right? The best case scenario is that the solution is 0, right? But however, that might not be the case. This is the worst case scenario, and I can be sure that I can do this, right? Because p, if it's equal to 0, I just return 0. Otherwise, if p is greater or equal to 1, I must use at least one pair, right? And I know that every single pair is either going to be this value or better, right? So worst case, this is my worst case value, right? So I know that this one, for example, is true if I want to return this result. True in that I can reach this result, right? But obviously I want to minimize. So what I'm going to do is I'm going to run leftmost binary search. I'm going to do leftmost binary search from in this range of values from 0 to the maximum minus the min num. Find the leftmost value that I actually can do, right? That way I minimize. And here's how we do it. L comma r is equal to min diff max diff, while L less than or equal to r. Let's do the binary search. Mid is equal to L plus r over 2. So now what we do is like, okay, this is mid, right? Let's say that we wanted to find p pairs whose maximum difference is at most this middle value, right? Remember, this is our range of values. So when we have mid is equal to the middle between L and R, we're trying to check if mid works, right? Can I get p pairs whose values are less than or equal to mid? Well, let's count. One way to count that is by saying, okay, how many pairs can I get from nums whose difference is less than or equal to mid? So this is why I sorted nums, because if you think about absolute value, ideally what you want to do is subtract numbers that are very close to each other in value, right? You want to subtract a 6 with a 6, which gives you a 0, right? You don't want to subtract a 9 and a 1, which gives you an 8, right? 1 minus 9 would give you -8, but when you absolute value it, it's going to be 8, right? We're dealing about absolute values here, so we want to essentially subtract numbers that are very close to each other in value. So that's why I sort nums, because I'm going to say, okay, let's look at the two smallest numbers. What happens when I absolute value, when I subtract them, right? And this is why this binary search idea works, right? Because all I care about is finding pair differences who are less than or equal to mid. Versus before, I was trying to find like, what are the best differences I can do. Well, I don't know what the best is, right? So I don't have anything to go off of. If I have a 3 and a 1, I'm like, okay, a difference of 2 is not that bad, but can I do better? I have no idea. Here, all I care about is, can I get pair differences or just less or equal to mid? So it gives me something to work with, right? So here what I'm going to do is I'm going to loop through all of nums. So I is equal to 1 because I'm going to do current index and previous index. And I'll say, well, I is less than n. Okay, num is equal to nums of I. Pair of num is equal to nums of I minus 1, right? Because here I'm going through the numbers that are side by side because nums have sorted, which means that numbers that are adjacent to each other are the ones that are closest in value to each other, which are the ones I can use for essentially minimum differences, right? And so this is the greedy aspect of the solution. So this is I'm leftmost binary searching over the range of values, but inside of the body I do O of n work, which is O of n greedy solution to find like p smallest difference pairs. So since I want the numbers to be as close to each other, that's why I have num sorted, and I just go through each pair of adjacent elements. So num is equal to nums of I, pair of num is equal to nums of I minus 1, and I compute its absolute value difference, and if it's less than or equal to mid, that is a working solution. So I'll do count plus or equal to 1 for the number of pairs that have the maximum difference less than or equal to mid. But now note that since I used index I and index I minus 1, I cannot reuse them in any other solution. So when I do I plus or equal to 1 and go to the next one, I might see, oh, the prev num and the current num actually work as well, and I would reuse an index twice. So that's why I do I plus or equal to 1, to make sure that I don't reuse the same index again. And then at the very end, we'll essentially have, okay, what are the number of, the count of numbers that can have, a difference that is less than or equal to mid, right? Well, that count, if it's greater than or equal to p, right, then that means we can indeed have p pairs whose maximum difference is mid, right, that are less than or equal to mid. So in that case, we're like, okay, let's look for even potentially better solutions, right? So let's look in the left subhalf, because we know, well, I could keep track of a variable here, but I know with leftmost binary search, when I return L at the end, it'll be the actual correct index. If you're really paranoid here, you could just have like, res is equal to mid, and then just return res at the very end, right? So here it's like, you could set res equal to r because max diff is always valid, and then every time you find a valid solution, say res is equal to mid, and then return res, and something like this will indeed work. If you're paranoid like I am sometimes, but I know that just return L with leftmost binary search will always work. Okay, so here we'll say r is equal to mid minus 1 because now we'll look in the left subhalf, right? We know that the solution works for mid, but since we want to minimize, we want to look for, can we do even smaller solutions? So we cut our search space in half by now only looking at solutions in the left-hand side for even smaller ones, right? Otherwise, if count is less than p, that means that, we're dealing with a number that's too small, right? There's not enough pairs whose maximum difference is less than or equal to mid. So we need to essentially loosen that constraint to make mid a little larger so that then we might actually have enough pairs to that will be less than or equal to mid, right? So in that case, we just search in the right subhalf, right? Current solution is invalid, which means all the solutions that are even smaller than mid are definitely invalid. So let's look in the right subhalf for actually valid solutions, right? And we just return the index L because again, we're binary searching over the possible range of values, and we're just leftmost binary searching to find the minimum one that is acceptable. And there we go, bada bing, bada boom. We have a nice and working 69% solution for this problem. So the main idea is basically just binary search with O of n greedy work inside of the body. And yeah, but otherwise, that's pretty much it for this video. If you did find it useful, enjoyable, and eager to perform, I'd highly appreciate if you left a like or a comment. But otherwise, I'll catch you next one. So till then, ciao, ciao, my friend. Bye-bye.